There are three main definitions of acids and bases that we need to go over in this video. The first is the Arrhenius theory. So this theory says that acids produce hydrogen ions, or H+, when dissolved in water. For example, HCl dissolved in water would form an H+ plus a Cl-. Bases produce hydroxide ions, or OH-, when dissolved in water. So an Arrhenius base would be, say, something like sodium hydroxide, which produces hydroxide ions when dissolved in water. The second theory that we need to talk about is the Bronsted-Lowry theory. A Bronsted-Lowry acid is a proton donor. So an example of a Bronsted-Lowry acid would be HCl. In this example here, if we react HCl with water, then the proton from HCl donates to the water to form an H3O+, which is a hydronium ion, plus a Cl-. The proton is transferred from the HCl, from the acid, to water, which is acting as a base. A Bronsted-Lowry base, then, is a proton acceptor. An example being ammonia, NH3. It will accept a proton from water, so it acts as a Bronsted-Lowry base to become NH4+, and then water, which is acting as the acid, loses or donates a proton to become OH-. There are some substances that can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base, depending on what it is reacting with. These are called amphoteric substances. Two examples would be water or baking soda. In the first reaction here, HCO3- plus H2O reacts to give H2CO3 and OH-. A proton is donated from the water to the baking soda, meaning that the water is acting as an acid and the baking soda is acting as a base. In the second example, it's the opposite. The baking soda, the HCO3, is donating a proton to the water. So this now is acting as an acid, and this is acting as a base. In reality, if we have baking soda in water, both of these reactions are taking place. Finally, the third theory is the Lewis theory. This is pretty similar to the Bronsted-Lowry theory, except instead of talking about protons being donated or accepted, a acid in the Lewis theory is an electron pair acceptor. An example would be BF3, AlCl3, other transition metal ions that form complex ions with small molecules. A base, then, is an electron pair donator. If we look at BF3, it is an acid, a Lewis acid, because it's going to accept a pair of electrons from the F- to become BF4-. That means that the F- is a electron pair donator, so in this reaction, it's acting as a base. When we talk about Bronsted-Lowry acids and bases, we usually talk about conjugate acid-base pairs. This is a pair of substances whose molecular formulas differ by a single proton. In this example here, we've got ethanoic acid reacting with water. In This example, the H from the ethanoic acid is being donated to the water to form a hydronium ion and this other ion here. So ethanoic acid is acting as the Bronsted-Lowry acid and water is acting as the base. Now this first conjugate pair here, we would say it differs only by a proton because it's missing a proton in this ion where it's not in the acid. So we would call this here its conjugate base. And that's because if we did the reaction in the opposite direction, this conjugate base is now the proton acceptor. It will accept a proton from the hydronium to form ethanoic acid and water. The base water has a conjugate acid. This would be its conjugate acid. It differs because it has one extra proton. And it's a conjugate acid because it's the same deal. If we were going in the reverse direction, it would donate a proton to this ion here to form water and ethanoic acid.